Hello everyone, this is the third lecture for Unit 1. So what we have been doing up to this point is we did a basic review in the first lecture about psychology itself, and we talked about how it's the study of mental processes and the behaviors that go along with those. We talked about how that was sort of a circular pattern, right? That your mental processes can affect your behavior can affect your mental processes, and it can work in a circular fashion. We talked about how psychologists follow the scientific method and why that is so important, because people are drawn to make certain errors like hindsight bias and things like that. In the second chapter, we started talking about the nervous system itself, and we talked about how it was divided up. We have a central nervous system, which is our brain and our spinal cord, but then we have this peripheral nervous system, which is doing tons of other things, like bringing in sensory information, using sensory neurons, or taking information from our nervous system, our central nervous system, out to our muscles and our glands in case we need to do something or move, or in other words, communicate with the endocrine system. If you remember, that was the best friend of the nervous system. So we talked about the peripheral nervous system. We talked about some of the brain regions and what they do and why they're important and where they might be located. We talked about the neuron itself and how the neuron is like a normal cell and that it has a cell body and a nucleus and some of those kinds of things, but that it has some very specialized parts. So this final part that we're going to do here, again, even though it's not located exactly in the same order in your book, I always like to go ahead and talk about this particular stuff after we've talked about the structure of the nervous system, the structure of the brain, particularly because we just spent all this time talking about what sensory neurons do and how all the interneurons in your brain and elsewhere are processing all the incoming information and helping you make sense of it and connecting it with your memory and doing all of these things, and how your motor neurons are constantly sending information out. And so in my mind, it just makes sense for the next thing that we talk about to be a little bit more about your sensory systems, since we just talked about sensory neurons. So that's why we're skipping a little bit ahead in your book, and I'm going to go ahead and talk about the idea of sensation and perception, and we're going to talk a bit more in detail about your different sensory systems. So that's what we're going to talk about in this lecture, is this idea of sensation and perception. First couple things are just a couple optical illusions that I want you to try to mess with. This one, I'll leave it on for a few seconds, but if you try to stare at the middle, see if you can get it to move. You may have to turn the lights on and off in your room or wherever you're watching this, but if you can do this in a dark setting, you'll actually see it might move a little bit. It's pretty neat. All right, you can actually even pause the screen and the effect should still happen, which would even just show you that there actually is nothing moving on my screen. Here's another optical illusion. I like to show people this, and I like to say, what do you see? Now, unfortunately, I don't get to actually talk to you in class, so you can't tell me what you see. But some typical responses that I hear are this. Some people typically tell me, hey, I see some circles. I see 3 circles. Or some people even say 3 Pac-Mans, and I say, yeah, that's good, that's good. Some people say they see 2 triangles. They see this one, and they see this one. Some of them say, hey, those 2 triangles together actually even make a star. And I say, great, all of that is wonderful, good job. Your sensory systems are working very well. But then I say, but you know what? There isn't actually a single triangle on this screen. There isn't actually a single circle in this image. What your brain did was fill in the missing pieces. Your brain connected this together to make the image of a star. Your brain assumed that the black triangle must have been on top, and that's why we couldn't see the rest of the red circle. In other words, your brain is wired to fill in the pieces, in this case, so that we see things like depth. We can tell that the black triangle must be on top of the other things. And that's absolutely okay that that's what your visual system experienced, because, right, that's how your system works. Right? Information comes in and then we process it and try to make sense of it. I'm going to give you those fancy words with those 2 things that we do in just a second. So what are we going to be talking about at first before we jump into the individual sensory systems like your eyes and your ears and things like that? Well, we're going to talk about what it means to sense the world. We're going to have to talk a little bit more about thresholds. We're going to talk about this cool thing called sensory adaptation, which you know what it is. You just didn't know there was a word for it. But going back to what I just said, let me give you some formal definitions for some things that I was just talking to you about. No matter what's happening in the world, no matter what you are experiencing, there's always going to be incoming sensory information, right? Some of it we want to pay attention to, some of it we want to ignore. Right? For example, when you're driving, right, you want to pay attention to how fast you're going. You want to pay attention to what the cars around you are doing so you don't get into an accident. You want to pay attention to the stoplights, that you stop when you're supposed to or you go when you're supposed to. Right? But you also want to be able to ignore other stuff that's going on around you so that you can focus on the important things. This is why our nervous system's ability to do these two things, sensation and perception, are so important, right? So our brain needs the ability, our nervous system needs the ability to do both sensation and perception. So let's talk about the definitions, and I've highlighted them in blue. The definitions that I want you to learn are highlighted here at the end here. So basically, let's start from the bottom. To represent our world, we have to be able to detect different kinds of energy in the world, various stimuli. Let's use your eyes for just a minute, because that's what we were using with some of those optical illusions. You have to be able to detect light energy. Light travels in waveform. It has to go into your eyeballs. It has to hit the back of your eyeballs, which is where the specialized receptors are, those specialized dendrites on those special neurons that will detect the light. Those specialized cells, those specialized neurons will ultimately send that information to the brain. And if you've studied that second lecture already, you will know that eventually it will hit the thalamus, right, coming through that reticular formation. It will go to the thalamus, and the thalamus will direct it to the correct location to be processed, which is the back of your head in the occipital lobe. That process is sensation. Sensation is purely just our sensory receptors and our nervous system picking up on energy in the outside world. So again, it can be light, it can be moving air, which is going to go into your ear and you're going to hear it as sound. It can be a chemical that gets in your nose and you smell it. It can be a chemical that gets in your mouth and you taste it. It can be something that touches your skin. But we have to be able to pick up on that energy. Right? We have to have specialized neurons that can do that, and we do. And then those neurons have to send that information to the brain. Sending it to the brain, collecting that information is called sensation. But that's not enough. Right? Just getting it to the brain is not enough. Your brain then needs to say, what is this? Your brain needs to identify it, recognize it, commit it to memory. And that part is called perception, right? So light coming into my eyeballs, right? That light is going to stimulate those specialized dendrites in the back of my eye. Those neurons are going to eventually send that message up to my occipital lobe. But unless my occipital lobe can say, oh, you're looking at a picture of a rainbow, or, oh, you're looking at a bird, or, oh, you're looking at a picture of a Ferrari, right? That incoming, that sensation didn't mean anything. So the perception is what helps us give meaning to objects. Even if we don't know what the object is, all right, we're still going to try to perceive it. We're going to basically then rely on memory. We're going to say, okay, it kind of looks like a bird. I mean, it's got wings. It's got a beak. I've never seen anything like that before, but I'm going to guess it's a bird, all right? That's still perception. Is trying to figure out that incoming information and figure out what in the world it is. So you need both pieces. You need the ability to bring the information in, that sensation, and then you need the ability to figure out what is this that I'm smelling? What is this that I'm hearing? What is this that I'm seeing? And that is perception. So make sure you get those two definitions. A couple other cool things that we can do related to sensation and perception. The first one is called bottom-up processing, right? Again, this is a little bit advanced, and if you go on to take biological psychology, or if you even really like this and go on to take neuroscience like I did in graduate school, you're going to learn way more about the visual system than you ever really wanted to know. But what's really cool about the visual system is that you have specialized neurons not only in your eye, but also in your occipital lobe, that their specific job is to detect certain shapes, certain objects. For example, faces. You have an entire brain region dedicated just to detecting faces. Right? And what happens is that incoming sensory information comes in, right? And then you need to put it together to make something meaningful out of it. So, for example, when you were a little kid and you were first learning letters of the alphabet, right? You learned that this was called a letter A. But what really is coming into your brain, the literal information that is being sent by multiple neurons, is one line kind of in this direction, another longer line in this direction, and a line in the middle. And what your brain has to do is reconstruct it. So this is what was sent in, sensation. This is what is perceived. And enough times of a little kid being told, when you see this pattern, it's called a letter A, you quickly learn, hey, when this comes in, I can then interpret it or perceive it as a letter A. That is bottom-up processing. The pieces come in from the bottom, all broken up, and your brain puts it together. Does that make sense? We do this some, again, particularly when you're learning language, right? Or you're learning some kind of symbols, or you're learning various things like that. But that's not the only thing that we can do, because eventually you've already learned a bunch of stuff, and you already can read and you can write, and you know what things mean, and you know what shapes look like. And that's when we get to do a second kind of processing, and that one is called top-down processing, right? Top-down processing, I'll describe it to you in a minute, but I'm going to show it to you first. So I've got a box here, and what I'm going to do very briefly is I'm going to remove the box, and what you're going to see is two words underneath the box, and then I'm going to hide it again. It's going to be super quick. All right, but what I want you to do, so pay attention, is I want you to look, and I want you to tell me what the two words are. All right, you ready? All right, here's the two words. Did you get it? Let's try it one more time. See if you can read the two words. All right, excellent. So hopefully as you're sitting there, you guessed what the two words are. Now, unfortunately, again, because we're online and not in class, you don't get to call out to me what you saw. But I can tell you from the last 10 years of teaching it and using this example, I hear two different things that people saw. Some people see the cat, and some people see the chat. And there are a few other things that I've heard, but those are the two most common. So if you heard one of those two, all right, no worries. You were just like about 90% of my students. And if you saw something else, that does not mean anything is wrong. It just means that you saw something else. So whatever words that you saw, all right, were there. But here's the interesting part. I'm going to show it to you again, but I'm going to leave it there for a little bit longer. See if the words that are here are the cat or the chat. See which one it is. Aha! The word the is there. So if you saw the, you were good. But that second word is not chat, and it is not cat. In fact, it's not an English word at all. It's C-H-T. But again, I've been doing this over 10 years. And all the time, every single semester, every class, every semester, people will tell me that they see the chat or the cat. And I say, why? Why do you think you saw that? And people go, well, Dr. West, you said it was going to be two words. And I'm like, you're right, I did. So what you did, because you were expecting words and you only got to see it quickly, you used what you already knew in your head. You used stuff from memory to make sense of what was there, right? Which is why you either filled it in, right, and made this an A, right, or you sort of quickly in your head, and this is another cool cognitive trick, you saw this as an H, but you needed to make it a word, so you actually kind of duplicated it in your head, so you got an H and an A for chat. Right? Either one makes total sense, and we do this all the time, and it's good that we can do this all the time. Right? This is how you can read a text message from somebody that's misspelled a bunch of words, because you can figure out, okay, I think they mean this. All right? A silly example that's a little bit R-rated, all right, but as I always find hilarious. I have a friend who, let's just say she likes to use a lot of cuss words, and very, very frequently she will text me the word duck. More than likely she did not mean the word duck, but again, I know what she meant because I can use top-down processing and I can figure out, spell checker changed it to a different word. Right? This is why those things that go around social media where it's like every bunch of words every single word is misspelled, right? But you can still read the whole paragraph. The reason you're able to do that is because of top-down processing. You're using things that you already know. So higher level mental processes like memory, reading skills to actually alter the perception. So in other words, you kind of ignore the real sensation that's coming in so that you can perceive something, you can make it make sense in your head to something that's understandable. It's a pretty cool thing that we do. All right, some other things that our brains are capable of doing are making sense of very complex situations. Now this is another one where you're probably going to want to turn off the lights so that you can see the image better, and you're going to want to pause this video so that you can look for them. But if I told you or if I asked you, what is this a picture of? Just basically, what is this a picture of? Most people say, okay, I see some woods. I see a rider on a horse walking with a second horse. And I'm going to go, yep, great. Right? But that's not all that we are able to see. Our brains are actually able to interpret even cooler things. We can find things, we can find complex images in something that on the surface looks fairly simple. So this is where I want you to pause it. I want you to pause it and I want you to count the number of faces that you see. I'll give you two examples. Here's one face. See the forehead, the eyes, nose, mouth. There's one face. Here's a second face. All right. The record that my class has found is 17. I actually don't know how many there are. Right? But the record that somebody said that they found one time was 17. So pause this, see how many faces you can find, and see how well you do, and then move on to the next step. All right. Now what we're going to do is start talking about your sensory systems, but there's going to be some terms and some traits that are going to be common to all of them. So we're going to do that, and then we'll jump into the individual systems. So there's three basic steps that all sensory systems need to be able to do. The first one is receiving the information, the light, the sound, whatever it is, and they need to have specialized receptors to do that. And those specialized receptors need to be able to transform that information into neural impulses or into action potentials. So step 1 and 2 is the beginning of sensation. Then that information needs to travel via axon and neurons to the brain, right, where it can then be interpreted, and that's perception. So all of your sensory systems are going to do this. So as we talk about the sensory systems, we're going to talk a little bit for each one about the specialized receptors. We'll talk a little bit about how those receptors transform, for example, light into an action potential or a chemical into an action potential, and then take that information to the brain. A couple other things common to all of the various sensory systems. Here's a few definitions for you. The first one is absolute threshold. Absolute threshold is the minimum amount of stimulus energy that a person can detect. So it's the minimum amount of light to where you'd be able to go, yep, I can see light. It's the minimum amount of sound to where you can say, yep, I can hear something. Minimum amount of chemical to where you can say, yeah, I smell it or I taste it. Minimum amount of pressure to where you can say, yep, I feel that on my skin. That's absolute threshold. Right? But right, we don't tend to rely on absolute threshold for our sensory systems. We tend to need more than the minimum amount of stimulus energy. Why? Because, right, there's so much other sensory information in the world that's competing. And that competing sensory information is called noise. Now, when people hear this, they tend to only think of sound noise, and that's the one you're probably most familiar with. For example, if you're watching this lecture, right, and you're listening to me talk during this PowerPoint presentation, it's probably easier for you to hear me if there's not a bunch of noise in the background. So if there's not a TV or a radio going, if people aren't talking behind you, it's a lot easier for you to pay attention to me. Why? Because there isn't as much noise. So your brain isn't having to sort out my voice versus all the other noise. But sound isn't the only one, right, that actually has this concept of noise. Right? Light, right? There's actually something called light noise, and we see this a lot. The coolest example that I have personally ever experienced is this. I love going out at night and looking at the stars. I just think it's really pretty. I think it's romantic, right? And I've lived down here in Rock Hill for most of my life. But I lived for a little over a year up in rural Maine. And when I say rural Maine, I mean rural Maine. The biggest city that most people have heard of is Bar Harbor, maybe Bangor. I lived 3 hours north of there. All right, I was almost up near the Canada border, really, really, really far in Maine, which is fine, and it was great for a year. Definitely glad to be back down south. I am definitely more suited for not snowy winters. But here's the point of the story. All right, I had seen the stars. I could pick out some constellations. I mean, I'm not like an expert at it. It's just something fun that I do, and I enjoy going out there, particularly in the summer. But when I was in Maine, I went outside to look at the stars, and I was beyond impressed because there wasn't a bunch of light noise. There weren't street lights. There weren't city lights. There weren't even house lights because my house was the only house for about a mile. All right. There was absolutely no light in my backyard when I turned off my porch light. And man, I could see so many more stars because I had reduced the amount of light noise. In fact, I was even able to see kind of the Milky Way. All right, it's sort of like a cloud-looking shape up in the sky. I was finally actually able to see that in real life because the noise, the light noise of the city and stuff that's all around was reduced. It was really, really cool. Now, I tell you all that to get to the third definition. And the third definition is the difference threshold. And this is primarily what we use on a day-to-day basis to pay attention to sensory information. The difference threshold is the difference, right, that has to exist between two competing stimuli before you can tell the difference. Right? So for example, right, if I know that I'm going to be speaking in a room where it's going to be really noisy, I'm going to use a really loud voice, or I'm going to use a microphone even. Why? Because I want my voice to be bigger, a much bigger difference than the noise that's going on, so that you hear my voice and it's clear. Right? You might do the same thing. If there's a whole bunch of noise and you can't quite hear your music, you're going to turn the radio up. In other words, you're increasing that difference threshold so that the stimuli you want to pay attention to is easier to hear or easier to see. All right. Does that make sense? All right. There's a whole culinary experience, right, where people will serve you these very, very fancy meals. And in between each meal, you're given this little bit of, I'm probably going to butcher this. You can see I'm not good on this, but I think it's something like sherbet or something like that. You're given just this tiny little spoonful of sherbet. And the concept is, right, it's supposed to cleanse your palate so that there isn't a bunch of leftover residue chemical from the previous dish, so that when you taste the next dish, you get the full experience. Right? So that little bit of cleansing there helps to reduce the noise so that the difference threshold is more exaggerated. Hopefully that makes sense. All right, I'm going to show you something. You do not need to graph this. I will never make you graph it or understand it, but I'm using the graph to make a point for the next term I'm going to tell you about. So I've told you about absolute threshold. And remember, we said that absolute threshold was the bare minimum amount of stimulus that you needed. So the bare minimum light or noise or chemical that you needed to be able to detect, all right, that sensory information was there. Mathematically, it's a tiny bit of a different definition. Mathematically, absolute threshold is the minimum stimulation that's needed to detect the stimulus 50% of the time. All right, and you would graph it like this. So this is lumens, which means it's the amount of light. So you go from absolutely no light, 5 lumens, 10, 15, so on and so on. And this is the proportion of the amount of times people say, yes, I see light. As you can see, there's variation among people, which makes sense. Everybody's slightly different. But the typical average absolute threshold for people, which is again where most people, half and half, will say yes, they see it, is approximately 11 or 12 lumens. All right, that's how they determine absolute threshold. Does that math make sense? Again, I won't make you explain it. I just want you to understand this graph so that my next term makes sense. Okay, so the next term is called subliminal threshold. Subliminal threshold is when stimuli are technically below a person's absolute threshold for conscious awareness, right? But it can still have a huge impact on us. And the picture that I'm showing you here represents a really cool study that was done looking at the effect of the type of music played in various stores. This is a particular grocery store, but they did it in a variety of different stores. And what they found is that if they played faster music, people walked around the store faster and tended to buy less items. If they played slower music, people tended to walk around the store slower and buy more items. So if you're a shop owner, right, you're going to want to play slower music in your store, right, if you want people to stay there longer and buy more things that way. Now, there's also this is called industrial organizational psychology. There's this whole other line of study that says, however, if your items are really expensive and you want people to buy them and not think too long, like, oh, should I really pay for this? You probably should play faster music. So they're tempted to go, yeah, I'm just going to get it. I'm just going to leave. All right. But again, the point of subliminal threshold is this. Let's go back to the original study. When they played slow music, people walked slower, bought more. When they played faster music, people walked faster and bought more. Then the people would come out of the store and the researchers would ask them, did you hear the music that was playing in the store? About half and half. Some people said yes, some people said no. But even for the people that said yes, right, they asked them, how fast was the music? And most people had no idea. They were totally wrong. But that doesn't mean that they weren't being affected by the music. In other words, the stimulation was coming in, the music wasn't so loud and overpowering, right, that you consciously heard it and overrode other things. It was just underneath that threshold, but it was just enough to where it was still able to influence you. So it was coming in what we call subliminally. It's pretty cool. All right, next thing that's also interesting. All right, this has happened to you, right? You just don't know it's happened to you. All right, sensory adaptation. Sensory adaptation is when you have diminished sensitivity as a consequence of constant stimulation. Okay, what in the world does that mean? Well, I've given an example here of a Band-Aid. If you put a Band-Aid on your arm, right, after a while, you're probably going to forget it's there, right? Unless the injury underneath still hurts, or unless the Band-Aid is pulling on your arm hair or something like that, you're probably going to even forget it's there. Why? Well, it's not because the receptors in your skin aren't still sending a message going, hey, something's touching me, something's touching me, something's touching me. What happens is your brain just starts to ignore it. Like, yeah, I know, you have a Band-Aid on, quit telling me. And we do this all the time, right? We do it with socks, we do it with shoes. People that put on ball caps, after a while, they actually forget their ball cap is there. And actually, it feels weird when they take the ball cap off, all right? That's what sensory adaptation is. Your body is constantly sending you information, right? But if that information isn't changing, if your sock is still in the same place, right, you're not going to pay attention to it. Your brain is going to be like, yeah, I know, your sock's in the same place, no big deal. And you probably won't even notice it's there unless something changes. So for example, unless your sock starts riding down and gets in between your toes and gets all uncomfortable. All right, that's sensory adaptation. Let me give you another example that this has probably happened to you. Have you ever gone to somebody's house or somebody's apartment or gotten in their car and you're like, oh my God, what stinks? Like, dude, this is terrible. Even if you didn't say it out loud to your friend, you thought to yourself, oh my God, it smells so bad in here. But then after like 5-10 minutes, you didn't really notice it anymore. Right? It's not that their house magically got clean. It's not that their car stopped smelling. It's just that your brain stopped paying attention to it, thank goodness. All right, so that's kind of one of those benefits of sensory adaptation, is that you stop paying attention to it after a while. So that is sensory adaptation. All right, something to think about. All right, there's a quote from your textbook that I want you to think about for a little bit, and I want you to hit pause, and I want you to think about this answer, because I am going to put this question in PackBack. All right, and I want you to think about what this could possibly mean. All right, here it is. We perceive the world not exactly as it is, but as it is useful for us to perceive it. So I want you to think about all that stuff I just told you. All right, and I want you to think, all right, what in the world does that mean? Is that true? And can I think of an example of it? I said I'm going to put this as a question on PackBack for you guys to answer. All right, so pause and give that some thought. All right, welcome back. So now what we are going to do is we are going to walk through the 5 basic sensory systems. Now you may read elsewhere that there are more. Some people will say 7. Some people even argue there's an 8th sense. They're not necessarily wrong, right? But for our purposes in this class, we are going to go over the top 5 sensory systems. We are going to talk about vision, hearing, or your sense of or sound. We're going to talk about taste and smell, and we're going to call those chemical senses because both taste and smell involve a chemical that goes into your nose or mouth. And we are going to talk about the sense of touch. And within the sense of touch, we are also going to talk about a concept called pain. So again, you may read elsewhere that there are more sensory systems than that, and that is okay. But for the purposes of this class, those are the ones that we are going to go over. So we're going to start with vision. As I said to you, every sensory system is going to sort of have this pattern. All right, you're going to need to know what stimulus is coming in. You're going to need to know the part of the body, in this case the eye, that holds those specialized dendrites on those special neurons that can detect the energy. All right, how that energy and information gets to the brain, and then other cool stuff about that particular sensory system. And again, we're going to start with vision. One more fancy word here. So, as a process of sensation, remember, sensation was bringing in sensory information, right, converting it into action potential and sending it to the brain. As part of that, that process also has a special name. It's called transduction. Right? Your sensory systems transduce stimulus energy like light or moving air into neural impulses. So those specialized dendrites take that energy and are able to transduce it into an action potential that can get sent to the brain. So keep that word in mind. Again, for light, for vision, the stimulus is light. All right? Light travels in a wave form, as do a bunch of other kinds of energy. If you look down here, there's a lot of different things that travel in waveform. X-rays, UV rays, infrared rays, broadcast bands, right? But you can't see all of those different waves. There's only actually a teeny tiny part of all the energy that moves in waveform that we can see. And if you blow it up, it's from approximately 400 nanometers to 700 nanometers. And that's what we call the visible spectrum. And if you use a prism to separate out Those different wavelengths, what you see and what you experience is what we typically call a rainbow. You're going to see a range of colors, usually from purples and blues on the 400 side all the way up to reds on the 700 side. All right, your eye is specifically designed to see what we call the visual spectrum. But not all eyes work the same way. Human eyes work in this way. Other organisms, for example, a bee, sees the world very differently, right? Because they can see a different part of this wave spectrum. Again, humans see the visible spectrum. All right, some other cool things. Because light travels in waves, there are two terms that we're going to talk about. So we're going to do a little bit of physics here, but because of this physics, you're going to understand why you can see the cool stuff that you can see. So we're going to talk about what wavelength means, and we're going to talk about what intensity means. Now, to give you the end of the story first, because light can travel in different wavelengths, you can see different colors. That's what I was talking about before, with the 400 nanometers being more purpley blue and the 700 nanometers being more reds and everything in between, greens, yellows, oranges, all those sorts of things. So because of wavelength, you can see color. And because of intensity, right, so how intense the light is, you can see brightness, the obvious one being dark versus light. But you can also actually see brightness that sort of mixes with color, and you can have very vibrant colors and you can have very pale colors. So intensity and wavelength can actually work together as well. So let's start with wavelength. Right? Wavelength gives us the ability to see hue. Hue is the fancy word for color. Right? Now, here's what wavelength is. These light waves, again, are traveling in waves. Just like in the ocean, you see wave after wave after wave. Wavelength is literally how long the waves are. So you would measure it from the top of one wave to the top of the next wave. And if it's a shorter distance, you're going to see something that comes more like bluish or purple. If the top to the top is a longer distance, you're going to see something more like orange or red. Now, you're also going to notice I have high-pitched sounds and low-pitched sounds here. You're going to see this information again when we talk auditory system because sound works the same way. But for light, wavelengths, right, the top of one wave to the top of the next, shorter wavelengths give you bluer colors, longer wavelengths give you redder colors, and the wavelengths in between give you all the different colors that we can see. So one more time here, again, more towards the 400 nanometers, you're going to see purples and blues. Towards the 700 nanometers, you're going to see oranges and reds. Right? And again, you're going to be able to detect everything in between for the most part. Right? So again, wavelength gives us the experience of hue, which is the fancy word for color. All right, the second part, the second little bit of physics here was intensity. Intensity gives you the experience of brightness. Low intensity light is going to look very dull or dark. High intensity light is going to look very bright or brilliant depending on your kind of color. So again, intensity is measured with how tall the waves are. So again, wavelength was top to top. All right, intensity is how tall it is. If it's a lot taller, it's going to be a lot more intense. It's going to be a very bright color. All right, again, you're going to see the same thing for sound later. This would give you a louder sound. A smaller amplitude, right, or a smaller height is going to give you a duller, a softer color, or a more dark, like you'll experience that it doesn't look very light in a room. It looks very dark in the room. Does that make sense? This is called amplitude. Amplitude is how high the wave is. Now, we hear amplitude, we more think sound, right? Like how many amps does this put out? That's amplitude, essentially. All right, but it works the same way for light. So how tall the wave is will give us a different amount of intensity. The next thing that I want to talk about a little bit is the actual structure of the eye. I am going to stay on this picture for just a moment. I'm going to talk through some of the parts, and then I'm going to skip ahead, all right, and I'm going to show you some definitions, all right, and I'm going to let you write them down. But before I do that, I want to talk about the parts of the eye. Now, hint, for a quiz or for an exam, I might have you label the parts of the eye that I'm going to go over here. So you're going to want to practice knowing not only what the structures do, right, but you want to be able to tell me where they are as well. All right, so this is an eyeball. This eyeball happens to be looking at a candle flame. And before I start talking about any of the parts, I want to show you something weird that your eyeball does. Look at this candle flame, right? Candles, you have the candle here, the flame is on top. If you turn it upside down, it makes a big mess because wax gets everywhere. So this eyeball is looking at a candle held upright. But look at what happens when that light comes into the eye and is projected onto the back of the eye. I told you that's where the receptors are. Look at what the candle is. The candle is actually upside down. Right? So here's something really cool about your visual system. The information that comes into your eye comes in upside down and broken apart into pieces. If you remember that bottom-up processing, right, where everything was broken up into pieces. Your brain, right, so that's sensation. Upside down, broken into pieces. That's the sensation that comes in. Perception, right, gives you the ability to flip it back the right direction and to see it in 3 dimensions. So your brain is actually doing a lot of the cool effects that you actually quote unquote see is done by your brain, not actually by your eyeball. I digress. There was a cool study that I did in college. I'll tell you about it very briefly. So when I was in college, they were doing this study. There's these glasses actually more like goggles that you put on, that you wear, that flip the image of what you're seeing. So when you put them on, everything looks upside down. So basically, I put these goggles on, and if I was looking at this candle, it would look upside down. All right, so if it came through eventually into my eye, it would be right side up on the back of my eye. Now that message is going to get sent to my brain, and my brain is used to doing what? Well, my brain is used to flipping what I see. So at first, everything that I looked at looked upside down. It was really freaky, right? And you weren't allowed to leave the lab. You had to sit in the lab. And what they were testing was how long it took for your brain to correct for the weird goggles that you had on. Let me tell you, this is the weirdest experience. So it took me several hours, I think it was almost 3 or 4 hours, before I, even with the goggles on, started seeing things upright again. And in between, as it was sort of figuring it out, things would like flip right in front of me because my brain was going, wait, what am I looking at? What is it supposed to be? Is it supposed to be upright? They wouldn't let you walk because if you can't even imagine how weird it felt. So to try to walk when everything looked upside down, it was just beyond bizarre, right? It was cool, but it was beyond bizarre. Right? So basically what they were testing was how long is it before the perception part of my brain figures out, wait, something's not right here, and flips it so that it was right. And then once my brain figured it out, it's no different as I just had on regular goggles. Everything looked normal. Right? But then it got weird again, because then they did the second half of the experiment, which was take off the goggles and see how long it takes my brain to revert back to helping me see right side up. Now, that part didn't take nearly as long. That part only took about 30 minutes. But holy cow, did I have the worst headache ever afterwards, because my brain was just like, what are you doing, woman? I'm trying to help you see correctly. Quit flipping things upside down in the wrong way. I'm trying to help you out. It was pretty cool. All right, let's talk about the parts of the eye. So this eyeball is looking at a candle, right? This candle is reflecting waves of light, and they're going to come into the eye. The first thing it's going to pass through is an outer coating, hopefully a clear outer coating. Sometimes it gets a little cloudy, not usually until you're older, but that clear outer coating is called your cornea. For any of you that are like me and wear contacts, that is where you're sticking that contact to. So when you open your eye and you put that contact on there, you're resting the contact on top of that clear cornea. Right? The clear cornea is a little bit of a thick layer. It helps protect so that hopefully things don't get in your eye and cause damage. It hurts like the dickens if it gets scratched. Again, sometimes when you're older, it can start to turn a little bit of a darker color. There's some whole disorders there. But for the most part, for most people, your cornea will stay this nice, thick, clear image the rest of your life, right? It's going to help protect the eye. All right, right behind that cornea, right, you're going to see two of my favorite parts of the body. Well, you're really only going to see one, but I'll explain what I mean in a minute. All right, you're going to see a colored ring in the eye. All right, some people have all different kinds of colors. There are so many different shades of brown and gold. There are blue, there are green, there are some that are kind of bluish green. Mine look kind of gray depending on the day. All right, there are tons of different colors. Right, that ring of coloredness in your eye, right, is called the iris. And it isn't just a ring of tissue. It's actually a muscle. It is the prettiest, in my opinion, the prettiest muscle in your body because it's usually some cool color. Again, some sort of shade of brown or black or gold or blue, right? So that's the cool part number one. The second thing that you will also see right behind the cornea is a big black dot. That black dot actually isn't anything. It's actually a hole. And that hole is called your pupil. So the iris is the pretty colored ring. It's a muscle. And because it's a muscle, it can expand and it can contract to make the hole or the pupil in the middle bigger or smaller. Right? And it does this on purpose so that you let in the correct amount of light. You don't want to let in too much light or you won't be able to see. If it's dark, you want to have it open really wide so that any and all available light can come in so that hopefully you can see, etc., etc. If you've ever gone to the eye doctor and they've given you some medication that purposefully dilates the iris, right? They'll say it's dilating the pupil, but again, the pupil is just a hole. So really what it's doing is it's dilating the iris so that the pupil hole gets bigger, right? You can imagine how weird that feels when you go out into the bright sun. They usually will give you these really dark sunglasses to wear afterwards because your iris is sort of paralyzed temporarily, so it can't contract and close and make the hole get smaller. It also makes it really, really hard to see and hard to focus the light, which is kind of funny. So those are the two cool parts that are right there behind the cornea. You have an actual part called the iris, that's the colored part. You have a hole, which is called the pupil, and that iris stretches or contracts or gets bigger or smaller so that the pupil, the hole, gets bigger or smaller so you let in the proper amount of light. Why? Because that light is going to be passing through the structure right behind it called the lens. And just like the lens in a camera, the lens's job is to help focus the light and make it a clear picture. And where it is focusing it onto is the very back of the eye called the retina. So the entire back of the eye is called the retina. And it is the job of the lens to focus the light directly onto the retina because the retina is what's made up of all those specialized neurons. The retina is basically just a big layer of neurons in the back of your eye. Your lens is pulled by a series of muscles. You do not need to learn those, but because it's pulled by a series of muscles, it can be pulled and stretched, or it can be relaxed and bunched up, so that depending on how far away or close something is, all right, you can get it to exactly hit the back of your eye where the retina is. All right, so the whole back of the eye is called the retina. I got three more parts to tell you. All right, within the retina, so within the whole back of the eye, you have three specialized parts. One of them is called the fovea. You can see it a little bit here. I'm going to show you another picture later. It's actually a small indentation in the retina. It's sort of like a little ditch, a little hole in there. The fovea is the point of central focus. So if you want to look at something and you want to see it clearly, you're probably going to turn your head to look at it. Because what happens when you turn your head is your eyes line up correctly so that the light that the thing that's coming off the thing you want to see directly hits that fovea. The fovea has the clearest vision. It's the point of central focus so you have the clearest vision. So, for example, if somebody goes, "Hey," and you turn and you go to look at them, right? You're going to turn your head, your entire head, and stare at their direction so that you can clearly see them. You're not just going to move your eyeballs a little bit. Again, you could probably see them a little bit, but you're not going to get as good and clear of detail because it's not going to be hitting the fovea. So the fovea gives you that clear vision. All right, another couple things that you're going to have. Remember, all of the cells that make up the retina and the fovea and everything here are neurons. All right. Now, they're specialized neurons that can detect light. The dendrites are specialized to detect light, but because they're neurons, they're still going to have a cell body, and they're still going to have an axon. Right? And that axon is going to be what sends the message eventually up into the brain saying, I saw something. Right? But again, you have hundreds and hundreds and hundreds of neurons here, right, in this retina. Each one of those neurons is going to have an axon. And instead of the axons leaving, right, in a whole bunch of places, they actually sort of all bundle up together and leave out of one location. We call that big bundle of axons that is leaving the optic nerve. Right? If you ever have heard the expression, I pinched a nerve, right? If you legitimately did that, what that really means is you applied pressure or you kinked, right, a whole bunch of axons grouped together, because that's what a nerve is a whole bunch of axons that are running around the same direction, going in the same direction somewhere. So all of your visual neurons, all of those axons leave the same place. They leave all in one big bunch called the optic nerve, and each eyeball has one. So each eyeball has an optic nerve that comes out to send information to the brain. But because of that, because all the axons leave in one location, you have what they call a blind spot. So you have this little tiny spot where there's just no room for dendrites. There's just no room here for cell bodies and dendrites. So that if light hits this part right here, you actually won't see whatever it is. Now, you have a couple things to your advantage. First of all, you have two eyeballs instead of one, and if both of your eyeballs are working, they're actually tag teaming. And what they're doing is they're constantly scanning the environment, whether you know it or not. They're twittering, they're twitching just a little bit constantly, right? They're sending the information to your brain, and your brain perceives, hey, there's a hole here, there's a piece of missing information, but it fills it in with the information from the other eyeball. So what you perceive is nothing. You don't normally experience your blind spot. Right? There's a really cool trick I'll show you in a few slides. It's actually in your book as well. So you can test your blind spot, but you have to cover one eye to do it so that the brain can't fill in the missing pieces. All right, so those are the parts of the eye that I want you to know. I want you to know the outer cornea. I want you to know the iris, right, which has a hole in it called the pupil. I want you to know the lens. I want you to know the retina. And specifically on the retina, I want you to know the fovea, the optic nerve, and because of the optic nerve, the blind spot. So I'm going to flip to this slide. I encourage you to hit pause and write down these definitions. Let's talk a little bit more about the lens. So again, I've given you the actual definition here. If you need to pause and write down that definition, you can. But I also want to talk about what the lens is actually doing and give you a formalized word. So I told you when I was showing you the picture of the eye that the light comes through the cornea, goes through the pupil, which is the hole made by the absence of the iris, and it goes through the lens. And the job of the lens is to be pulled and stretched by a series of muscles so that the light exactly hits the back of the retina. All right? That process of pulling and stretching and changing shape so that the light always hits the back of the retina is called accommodation. And if you want to test this, you can actually see and experience your lens in motion. Here's how you do it. You hold your finger up in front of you. So make like you're holding up the number 1 finger in front of you. All right, hold it about 6 inches or so away from about the middle of your face. All right, and stand facing a wall. Then what you're going to do is you're going to stare at your finger until it becomes crystal clear. And then without moving your finger and without moving your head, move just your eyeballs and look at the wall behind you. All right, behind your finger, until it becomes clear. Then move your eyes back to your finger until it becomes clear. Move your eyes back to the wall. Move your eyes back to your finger and back to the wall. And you can do that as many times as you want. But what you'll see is it takes it just a fraction of a second, right, or maybe longer if you have visual impairments like I do with my contacts. It also might take it a little bit longer if you've been having an adult beverage. It might take it a little bit longer if you're tired. There's several things that can take it a little bit more time for that lens to accommodate. But what you're going to see is that lens is going to be busy stretching and flattening and stretching and flattening as you're going back and forth, and your eye is going to be going, what are you doing? Stop doing that. But that's what accommodation is for, and you are constantly doing this as you are looking around the world. As you're looking at things close up, it's going to accommodate one way, and as you look at things further away, it's going to accommodate another way, and your lens is constantly stretching and pulling and moving in order for you to do that. And again, the reason that's important is because you need that light to hit the very back of your eye on the retina, because that's where all of those neurons are. That's where all of those specialized neurons with specialized dendrites are to detect the light. So let's talk a little bit more about the retina. Again, if you want to pause and write down the definition here of retina, I suggest that you do that. But the retina, again, is just the light-sensitive inner surface of the back of the eye. So the retina is the entire back of the eye. And when I was talking to you earlier, I actually oversimplified a little bit. There's actually a whole bunch of different kinds of neurons here. And if you find this stuff interesting, I highly suggest that you go on and take biological psychology, because you'll go into this in a whole lot more detail. But the general idea of what's going on here is that you have certain cells, and we call them rods and cones, and these are specialized neurons that are able to take the light and convert it into action potential. Those rods and cones pass it on to a couple other kinds of cells, and then the neurons of those cells, the axons of those neurons are what leave out that optic nerve. All right, so again, a little bit oversimplified what I told you before. There's actually tons of different kinds of cells. There's also some things called amacrine cells and horizontal cells. There's a whole bunch of kinds of things. All of them are different types of neurons. All of them are needed to help you see everything that you're able to see. But the number one thing that we're going to focus on for this class is the very first stop, which is the rods and the cones. Now, something else weird that I want to show you about the retina, right? As the light is coming in, so you can see here's the eyeball, here's the iris that's colored, there's the pupil, that's the hole. The light comes in and it hits the retina. Look at what the light has to do. The light actually has to pass through all of these other cell layers first before it hits the rods and the cones, the specific neurons that can detect light. That's a very weird phenomenon, right? But it's something that absolutely happens. But that's another thing that I'm going to make a point of in just a minute as to why your fovea is shaped the way that it's shaped. But the retina in general, the entire back of your eye, is made up of a whole bunch of different kinds of neurons, and the ones that we're going to learn for this class are rods and cones. All right, a little bit more about the optic nerve. So again, the rods and cones have passed their message on to various other kinds of neurons. And all of those axons from those neurons gather together and leave out one location called the optic nerve. So the optic nerve is what's carrying the neural impulse, or that action potential, from the eyeball itself to the brain. Because of the optic nerve, you also have a blind spot. So there's that definition there. And again, if you need to pause and write these down, that's fine. But as I also told you, you have one spot on your retina called the fovea, and that spot gives you the clearest vision. So again, if you wanted to see something very clearly or pay attention to something, you probably turn your entire head to look at the object, because that's what's going to help you to see it the most clearly, because that's what allows the light to actually hit that fovea. And I also told you the fovea was sort of indented or made like a little ditch or a little hole. Here's why, right? There's two reasons why the fovea gives you very, very clear vision, right? The first one is because of this indentation. All of those other kinds of neurons that I told you about that were there, so if you go back, remember all the light had to go through all these other kinds of neurons? In the fovea, those cell bodies of those neurons purposefully grow sort of to the side. They almost leave an extra area of unexposed, right, rods and cones. Right? So this is what makes it easier. So the light doesn't have to go through all of these cell bodies as much. It can just go straight there and interact with those cells that are there. And that's the first reason why you get such clear vision in the fovea, is because of the way that the cells grow. I'll tell you the second reason in just a minute. As promised, here is a test for your blind spot. Now again, this might be a little hard to do on the computer, and if you are going to do it, you're going to need to pause the screen so you can do it. But what you need to do is cover your eye, all right, and then move your head closer or further away from the computer screen while staring at the black dot. And you'll get to a certain point where you will not see the car anymore. Now, if you keep both eyes open, it's not going to work because your brain is going to use its cool power, all right, of perception to fill in the gaps. But if you close one eye and don't give the brain that ability, you will actually find that the car will disappear. That's your blind spot. And again, the reason you don't see it there is because when you get in that exact spot where you can't see it, the light that's bouncing off your computer screen from the car is landing on the optic nerve in your eye, which is why you have a blind spot. So test that out for yourself. All right. A couple other things that I want to talk about. I told you the two kinds of cells, the two kinds of neurons I wanted you to remember were rods and cones. Let's talk about these two types and why you need two types of cells. Now, collectively, they are called photoreceptors. Photo is a fancy word for light, so it literally means these are light receptors. So those specialized dendrites are what are receiving the light energy. And I really wasn't kidding when I said that you have tons and tons and tons of neurons in the back of your eye alone. Cones, you have about 6 million. Rods, you have about 120 million. And that's just the rods and cones. That's not all those other neurons that I was talking about. You have tons of neurons in your eyes. But here's the second reason, right, why the fovea, right, is so clear. So not only is it because of the way the cells grow, but it's also because that's where you find the majority of the cones. The cones are located in the center of the retina. That's the fovea. They're not very sensitive in dim light, but cones are responsible for helping you to see color, and cones are responsible for helping you to see detail. Right? So if you wanted to see something in fine detail, if you want to see the color of it, you need to turn your head, you need to directly stare at it so that the light hits that fovea, that center of the retina, so that it can interact with your cones. Now, what are the rest of the cells doing? Well, the rest of the cells, and actually it's most of them, 120 million of them, are located in the periphery. So they're in kind of the rest of the retina. Right? They are highly sensitive in dim light, which means that even when it's dark outside, even if you can't quite tell what color something is, right, you can still see the overall shape. You can see if it's moving. Right? So rods don't give us color and they don't really give us detail, but here's why they're important. Right? If I'm standing outside and all of a sudden an object comes towards my face, what do I need to do? Well, I need to do several things. I either need to duck or move my head, put my hands up if I can. If nothing else, at least close my eyes so I don't get damaged. All right? All right, but does it matter if it's a rock or a baseball that's coming at my head? Do I need to know which one it is before I decide, hey, I should block my face, or I should duck, or I should move my head? No, doesn't matter at all. The point of our rods is that they are quick responding to motion. All right? Not just because stuff is coming at your face, although that's a very good example, but our rods help us to tell if something is moving and the overall shape of it. So I can see, oh, this is some kind of object and it's coming towards my face. I need to do something about it. And it's only later, right, that you're going to look on the ground to use your cones to go, oh, that was a baseball, or oh, that was a rock. All right? Because again, in the heat of the moment, it didn't matter what it was. You just needed to get your face out of the way so you didn't get damaged, you didn't get hurt. That's what the rods are for. Motion, detection, how something's moving, how fast it's moving. All right, now combine that, because you have both, we're typically able to see very complex things in a very complex way. So those are the photoreceptors. Those are what I want you to remember. Okay, so we've got a whole bunch of neurons. They're sending their axons out of the eye via an optic nerve. So here are two eyeballs. Each eyeball has an optic nerve. All right, those optic nerves, all right, do a little bit of crossing over, all right, and it will eventually go to the thalamus, and then will eventually go to the back part of the brain. So remember, we said incoming sensory information, all right, comes in through the reticular formation and then goes to the thalamus, and the thalamus sends it to the correct area of the brain. So here it is. Here is that occipital lobe that visual information is sent to. Now again, if you find this information interesting, take biological psychology. You'll learn a whole lot more about this idea of crossing over and this optic chiasm and all this stuff. But the basic idea is this: because our eyes do this, this is what helps us to then ultimately perceive 3D. And it's also what helps us sort of to fill in the pieces of our blind spot, because we have this cool sort of crossing over. All right, but our visual information will ultimately reach the back of the brain to be processed. A couple other cool things that I want to talk about with vision specifically. The first is a cool thing that you can do. You can see colors. If you remember back, we said you can see colors because of the wavelength, but we also see colors, we've now learned, because of our cones. It's those cones, all right, that are detecting the wavelength of the light and allowing us to see color. And for years and years and years and years, there were groups of psychologists that argued back and forth as to how exactly those cones helped us to see colors. And there were two major theories that sort of came out from that. Now, the end story is both are true, just sort of depending on the situation. But I'm going to tell you quickly both the stories. The first one is called the trichromatic theory. Tri meaning three, chroma meaning color. So basically this is the three-color theory. It was proposed by Jung and von Helmholtz. You do not need to remember their names, just remember the trichromatic theory. But what they suggested is that the cones in your eyes are sensitive to three different colors. You have some cones that are sensitive to red, some cones that are sensitive to blue, and some cones that are sensitive to green. So that if green light is coming into your eyeball, the green receptors, the green cones are going to be activated and send that information to your brain. If red is coming into your eye, the red cones will be activated and will be sent into your brain. If a different color, for example, orange or something, you're going to get a different combination of all three of those receptors, just not nearly as strong as if it was pure blue or pure red or pure green. And because of the different combinations, that's how your brain then interprets all of the different colors that you see. All right? And some people said, yeah, that makes total sense. All right? But there was a whole other group that said, wait a minute, all right? There's something to it. But here is some evidence for the idea of the trichromatic theory. Unless you are colorblind, and the number one thing that makes somebody colorblind, or not the number one thing, but the number one issue that most people that are colorblind have is they mix up reds and greens because the red and the green cones aren't formed exactly correctly. And they would not be able to stare at these circles and identify the numbers. So if you are not colorblind, or if you have a good enough computer screen, you can see that this says 74, and this says 45. Again, if you had a problem with this test on the computer screen, do not assume that you are colorblind. It's probably just a side effect of this particular slide and your particular screen. This is why you get some of those weird effects that are going around social media, like is this dress blue or is it gold or something like that. However, if you legitimately are concerned that you might be colorblind, that's something you could discuss with your doctor, and your doctor could give you a formalized version of this test called the Ishara test. Okay, that was the first group. All right, the trichromatic theory, that there was three kinds of cones, and depending on the different ratios of how they were activated, you would see different colors and all kinds of things. All right, and again, we know that that is true in some situations. But here's the other group. The other group came along, and the other group said this. The other group said, no. There are cones, yes, but they pair up in opposite colors. So each cone is sort of responsible for detecting opposite colors. And the colors that would go together would be black and white, red and green, and blue. I said that wrong. Start over again. Black and white, yellow and blue, red and green. So black and white, yellow, blue, red, green. Black and white, yellow, blue, red, and green. Now, to show you how this works, I'm going to demonstrate, but this is one of those weird effects of the way computer screens work. These should actually be green lines, but again, because of the way computers put out a slightly weird version and color of light, they probably look a little blue to you, but they really should be green. Now, what I want you to do is to stare at the black dot in the middle. All right, I'm going to count to 10. All right, you're going to stare at that black dot. It will work better if you turn the lights off in your room. Stare at the black dot. And then what I'm going to do is I'm going to take away the image. And I want you to see what you see on the screen just by staring at the white screen. So let's count to 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Do you see it? Do you see the after image and the after effect? It should look like the American flag. It's a pretty cool effect. All right. Again, that's the opponent colors theory, is that colors work together as opponents. So black and white, blue and yellow, red and green. Again, also true, also correct, just depends on the situation.